Alright, I think I should be live now. Just trying out the hotkeys for the first time ever. Alright, there we go, I am live. Cool, very nice. It doesn't look like anything's showing up. Okay, there we go. Awesome, alright. So today, the plan is to start looking into multiplicities in Idris 2, because last time I wanted to do Idris 2 stuff, I didn't quite get a chance to look into it, so I think today will be an Idris 2 day, so I guess if anyone's watching this in post, since I doubt anyone's going to actually watch this thing live. Whoa, okay. I hope that isn't super loud, those Windows errors, because they're super loud for me. Let's see, can I turn down the volume a bit? Maybe that'll fix that? Okay. Anyway, yeah. Okay, why does it keep making these noises? Stop it. Stop it, Windows. Really weird. Okay, that was less loud though, so I'm okay with that. Idris, right. So in case anyone's watching this in post, I'm probably going to do a very basic rundown of Idris first before I really dive into multiplicities here. Doing a little rundown of what I know about, I guess, linear logic, and yeah, we'll see where things go from there. So this is Idris. This is just an Idris file that I have here. Obviously, I have main. This is basically a hello world kind of program. It just prints out hi. So the function for doing that is put string line, same as in Haskell. You'll notice this type signature here. We're defining a function called main with type. So this colon means with type. And the type is IO unit. So unit can be kind of thought of as like void in Java or other, more mainstream languages. It's a bit different in some ways. There are very subtle differences. If you're coming from Rust or Scala, this is pretty familiar stuff. It's just a singleton value, or, well, singleton type. And it holds a single value which basically contains no information, and you kind of just use it when you have a function that just returns essentially nothing. There's an actual empty type when you have functions that just don't return at all. We're probably not going to be playing too much with those at all today because well, this is Idris and totality is nice, and we don't really want to have programs that don't terminate, otherwise the termination checker won't be happy. And the other part of this is this IO. So Idris, like Haskell, is a purely functional programming language, so if you want to do any kind of IO or side effects, you need this IO type constructor here. So yeah, the type of main will be IO unit. This is pretty common, and that's the definition. This is the function body. So again, we put down main. We say that main is equal to this, and anything on the right hand side of this equal sign is the actual function body. As you can see here, I have a function called foo. Takes a natural number, returns a natural number, and because it takes an argument and then returns something, we have to actually put the arguments on the left-hand side of the equal sign here. So the reason why we're allowed to do this, or the reason why we do this way, is because sometimes we want to actually pattern match. So for example, if we want to say look specifically for the number 0, we can put a Z there for the 0 constructor. We return 0 in that case, and this will essentially catch everything else. Or we could be more specific, I guess, and say if we have like the successor of some value, then we return its predecessor, right? So this is pretty simple stuff. As you can tell, natural numbers are recursively defined, right? Like 0 is the base case, and every number can be described as like one more than some previous number. And that's pretty much about it. We could also make this like a Boolean function, right? We wanted to take a bool and return a natural number based on that. We could do something like, say, false, so we could take the Boolean value and pattern match on the different variants we might have of Boolean. So you can kind of think of this as like pattern matching in Rust or Scala. Sort of like a switch statement as well in Java, where we just kind of switch on the argument type, or not the type, but you know, if you had like an enum in Java, you would switch on the different variants. Like we could have, I don't know, like a weekday or something. Nice, I typed weed. We could do like Monday. Oops, not monad-a. Monday. See, when you do too much functional programming, then you start typing monad everywhere. It's just a bad habit. Thursday, Friday, that kind of thing. We could take a weekday here, right? And then we could switch on the different variants. So we could have like Monday, we could have Tuesday, right? We return different values for each. Like maybe Monday is 0, maybe Tuesday is 1. So they have syntactic sugar for this. I think if you put like 0 here, it'll also work. Pretty sure about that. Wednesday, let's see, 2, and yeah, and so on and so forth. Here, let's just map the rest of these to just to show. I think this should compile. There shouldn't be any issues with that. Yeah, and also I think I have everything set up here to... Oh, here we go. Yeah, so I have the Idris to Vim plugin set up, and you can do some pretty cool stuff like auto-implementing functions with proof search or checking the types of things. So here I just did a type check of foo, and it couldn't parse the declaration. Undefined named foo. Why is that? Yeah, maybe that's not allowed. Because I do have weekday and I have nat here. I did define weekday up here. That's interesting. Let's just test checking a whole. Parse error at line 1. Okay. I'm starting to think that this might be a problem. Let's delete that for now. So this should tell me the type that I should put in here. So yeah, these things are called holes. You put a question mark in front of it. You can name it whatever you want and call it foo bar. And essentially what it does is it says that this part is unimplemented. Similar to what you might do in Java by throwing like a not implemented exception, or I guess C#. I think Rust might have something for this called like unimplemented, or I think some people just like to use panics for that instead. Scala has like the triple question mark, but this is a little bit more powerful because you can actually scan it and see what type is required there. So here it requires a natural number, or nat. So now we know that we can fill this in with like 3. Let's write that. And let's see, can I scan foo now? Yes. So foo is of type weekday to nat. And of course, because it actually has to type check like the entire file, we can tell that this code compiles. So that's pretty cool. Like earlier it was giving me errors even though this thing was all defined correctly, and that's because it couldn't compile the data definition I had above. So that's pretty cool. Let's do the whole thing again. I just want to show off something else really cool. We'll hit \s, And there you go. It automatically implemented it as 0. So that's proof search at work. That might seem a little bit confusing at first, but essentially what \s does is it looks for a value that matches the type that is expected here. So this whole needs to be of type natural number, and so Idris, when it does a proof search, just tries to look for any value that fits nat. And of course, the simplest value it can find is the base case of nat, which is just 0, so it fills it in with 0. Pretty basic stuff. The reason why it looks for any value is because types can be thought of as propositions. So in logic, you don't have a proof of a proposition unless you actually have a value for it, or like an actual proof. This is the case in constructive logics, at least. Most people are familiar with classical logic, where you have two values, true and false, for every proposition, but that can lead to some issues. So Idris supports something called constructive logics, and in constructive logic, you want to make sure that if you want to prove something, then all you have to do is find some value of that type, or some proof of that proposition. There's a correspondence there between proofs and values and types and propositions. So in this case, because nat isn't really a proper proposition, it just looks for any number, it finds 0 and says, okay, that's a valid proof of nat. 0 is a natural number. That's the proof of nat. If you're doing something a little bit more complex, like, I don't know, checking if, 2 is an element of some list, and you want to provide a proof of that, then, yeah, that's the kind of place where proof search becomes more useful. In this case, it just does a very basic auto implementation that doesn't make sense at all in any context. So you pretty much want to use proof search exclusively for functions that are incredibly well specified to a point where there's only one way to implement them, or for their primary use case of just searching for a proof for some proposition. It's usually pretty basic, and most of the time you can kind of figure it out yourself. Sometimes there's multiple different options, or there's multiple different implementations. Like maybe you are trying to implement a very specific kind of function, and you want to look for multiple different implementations. And I think there's some kind of keyboard shortcut that lets you hammer through the different possible implementations. I actually don't know if that's something that is here. No. Yeah, I think it is possible in Idris too. I've seen GIFs on Edwin Brady's Twitter showing off that functionality, where you can just kind of cycle through all the different implementations that might be possible and then choose one. That looked pretty cool, but yeah, I don't know what the shortcut is for that. I do have the Idris 2 Vim plugin, so I assume that I have that functionality somewhere, but it's not something that I've really learned. So yeah, that's pretty much everything to learn about functions in Idris, I think, or at least the basics of functions. There's definitely a lot more to learn about functions in Idris, especially because it's a dependently typed language. But these are kind of the basics. I'm not going to get into dependent types, I don't think. Maybe? Well, we'll see. It depends on how stuff goes with the multiplicities stuff. So another thing I want to talk about is data definitions. So as you can see, I kind of defined an enum up here with this data keyword called weekday, and it has these different variants, Monday, Tuesday, etc. So if you're coming from Java, this is pretty familiar to you probably. Most languages have some kind of enum structure like this. That's very, very basic. We have something a little bit more powerful in Idris. We can actually we can actually give each of these constructors, or I guess variants, their own values, I guess. So we could say Monday requires some kind of integer. No, this thing will have some argument. Actually, let's make it a natural number just to make this easier. And now we can return that. This doesn't really make sense, but let's start over and implement some kind of error data type, I guess. So maybe we have some kind of error type for our application. Maybe we have like a parse error, and we want to have some text that goes along with it, right? So we have a string. Maybe we have, I don't know, HTTP response error, and we want some kind of error code that can be like a natural number, and we want to have some text that goes along with it, so we can add a string as well for that. And essentially, if I want to actually handle the error, I can take the error, we can return, I don't know, a string. Let's use this handy shortcut that'll just generate that for us. So that's another cool thing about Idris. If you like press \A on a function name, it'll just automatically generate these cases, or at least one case. I think if I \C on the argument, yeah, it splits it out. That's even cooler. So it splits it into the two cases, and yeah, now I can just implement this one. So if I get a parse error, whoa, don't want to do that. Then I need to return some kind of string. I can say, oh no, parse error. And I believe concatenation is probably like this. I want to say that's how you do concatenation. I don't remember. Let's type check this to see. Oh yeah, that type checks. So yeah, this is just going to return this string, and obviously at the top level here, if we wanted, we could just, you know, call that and then print it. And for the HTTP response error, we might want to do something like, say, I don't know, oh no, HTTP response error. And we'll have like the error code, which could be show k. So what show does is it essentially is like a two-string method. If you have a type that implements, I think it's like the show interface, then you're allowed to call show, and that'll just convert it to a string. We could do a little bit better here with the names. We could call this, I guess, response code or something. Error message. Oops. Still not super familiar with Vim in that way. Still messing up my inputs, but oh well. Response code. And I think we can also even just add a space here. Error message. And we'll just tack on the error message. And you probably actually want to see this in action, don't you? Okay, let's try some stuff here. So how am I gonna do this? We need to construct an error, of course. Yeah, we'll have some function that actually returns an error. Let's see. Make HTTP response error. All that's going to do is return an error. As usual, we can do this to get the implementation real quick. And what I'm going to do is just create one of those. Give it a 404. And we'll say, I don't know, page not found. So now, if I'm not mistaken, yeah, I should be able to just do something like this. So I'm gonna explain that dollar sign in a minute. Just give me a second here. I just want to try running this first. Handle error. There we go. And now that should be fine. Actually, let's type check this. All right, that's fine. So if I go Idris 2 test.iter, you can do exec main, and there we go. Now it prints. So what just happened there? So Idris 2 opens up the REPL. You give it a file name, an Idris file specifically, and it'll load up that file. :exec allows you to run a function. The function I want to run is main because that's the one that can be executed, right? It returns IO unit. And yeah, when I run the program, it says, oh no, HTTP response error. Error code 404, error message, page not found. So yeah, that's pretty much it. Obviously, this isn't like the best way of doing things. You'd probably want to, you know, do like an error print line to the console instead of just, you know, doing a regular print. But I just wanted to show off how that worked. Now I'm going to get back into Vim here. We're going to show what this dollar sign's all about. So the dollar sign's actually really simple. A lot of people kind of get scared of Haskell and Idris because they're like, oh god, syntax, it's so weird and crazy and wacky, all these crazy operators. The dollar sign's one of the more basic ones. All it does is it allows you to, you know, avoid doing this. And the reason why I wanted to avoid doing that is because then I don't have to jump to the end here and like add another closing parenthesis. That's pretty much all there is to it. So if you want to avoid that, you can just put a dollar sign here, and now you don't have to add the 2 parentheses. Yeah, that's the, I guess, intuitive explanation for that. So yeah, that's a lot of the basics of Idris out of the way. You'll see that this isn't the only way to define data types. Commonly, you'll also see something like, I think it's like this. I think this is right. I might be completely wrong here, so I'm gonna actually comment this out. Comments are done with this double dash. Oops. Just tried to go a little too far there. Okay, wait. Parse error. So this is pretty similar to the above this is going to be an equivalent definition to the above. It's a different syntax. You might be wondering, why do we have a separate syntax for this? And truth be told, I'm not entirely sure. I know that maybe some people might think that this one is more convenient, like this top syntax. But in general, you can define every single data type with just this syntax. You don't have to do anything special. You don't have to do this. Every single data type can be defined using this second syntax here. So this syntax is actually strictly more powerful than the above syntax because you can actually use this to define inductively defined types. So you could actually define like an inductive proposition that checks, you know, if you have like an even number, that kind of thing, using dependent types. So that stuff is pretty interesting. Not going to get into that. I just want to show that this is an alternate syntax that can be used to define simpler types like this in a different way. It's just a syntactic thing. And if we close this, oops, I didn't write. Same thing happens. Nothing else had to change. So yeah, that's just proof that this thing is equivalent to this thing. And yeah, it's a complete drop-in replacement. No issues there. Hopefully that covers enough Idris 2 for people who are new, just to understand what the heck is going on here and what I'm doing. So now I'm going to move on to, I guess, looking at linear logics. I'm just going to put a bunch of space here so I can I guess, draw images with my cursor. So, I guess I'll talk a little bit about propositional logic, just as a recap for people if they aren't, or I guess if you're not familiar with propositional logic, this might be a very, very basic introduction, but essentially, in logic, we can have these kinds of statements, these propositions, I guess, like, I don't know, if X is mortal, then, like, wait, no. I think I have this backwards. I think it's like if X is a man, X is mortal, that kind of thing. Yeah, we kind of have this sort of thing going on in logic often. In linear logic, we might have something else, like if I have $1. Well, that didn't space out as well as I thought it would. Then I can buy a cookie, right? And the difference between these kinds of approaches is that in this one, right, if we apply this rule to a human who is a man, right, and we can conclude that they are immortal, it's a bit different from having $1 and then getting a cookie, right? In this logical rule, let me just like mark this as like this is linear logic, and this is my basic understanding of linear logic. This is regular like propositional logic. This might be more predicate logic because of this, but whatever. I'm kind of fudging things here. Don't mind me. Probably not the best thing to do, but yeah. If you're a real stickler for the rules, don't listen to me. But essentially, the key difference here is that you're spending resources in linear logic, right? Like there's actually like a state change here. Once I spend my $1 for the cookie, I don't have $1 anymore. Whereas in this case, if let's say I am a man, then I am, and I conclude that I am mortal, it doesn't mean I'm not a man anymore. It just means that, you know, I can conclude both of these things. I can reuse this this assumption essentially. Like, so if I have $1 and I spend it to get a cookie, I lose it. In this case, I don't lose the thing above the line, and that's pretty much it. It's linear logics allow us to actually model state changes. So if you've ever read what's his name's paper, Philip Wadler's Linear Types Can Change the World paper, that's pretty much what that's talking about by, you know, change the world. I mean, it kind of has a double meaning because linear logics are quite powerful. You can do a lot of interesting things. Obviously, Rust has done some interesting things with affine type systems, which are very closely related to linear type systems. So yeah, there's that double meaning of it allows you to change the state of the world, but it also could, you know, change the world of programming forever, that kind of thing. So that's a basic rundown of the core concepts that I think are going to be relevant to multiplicities. So now let's get into multiplicities proper here. So quantitative type theory is a relatively, I guess, new thing. It's something that was added into Idris 2, as far as I know, where you can actually add these multiplicities to variables, which essentially say that that variable can be used X number of times. The reason why I was explaining linear logic is because the way that you would implement a linear logic in programming would be to say that everything has a usage of 1. So you can use it exactly 1 time. That's kind of like spending the $1 for the cookie, right? If I haven't used it, I still have the $1. If I use it once, I lose my $1 and I get a cookie instead. And maybe we could spend the cookie by, you know, saying I eat the cookie and then I have a full stomach, right? So then I'd lose the cookie, but then I'd gain a full stomach. So we could have another rule for that or something. I don't know. you can do this for like exchanging currencies as well. Like if you have 4 quarters, you can get $1 out of that, but you lose the 4 quarters, of course. Yeah, that's pretty much how that relates to multiplicities. Quantitative type theory is sort of a little bit more broad than just linear logics or linear type systems, because now you actually can specify more than just a single 1 for everything. You're allowed to specify 0 here, and there's also this unrestricted. So that gives us the same behavior as Idris 1. So yeah, back in Idris 1, everything that I wrote up here will compile in Idris 1. You'll see that I don't have any multiplicities on any variables here. That's because every variable can be used as many times as you want. But with Idris 2, since Idris 2 is based on quantitative type theory, you can now start specifying how many times things are used, or at least that's my understanding so far. I actually haven't looked into this, and I don't really know how it works, and that's kind of the main reason why I'm doing this stream, is because I wanted to learn about it. So yeah, without further ado, let's start diving into this. So yeah, every variable in Idris 2 has a quantity associated with it. A quantity is 1 of 0, which means the variable is erased at runtime. 1 meaning the variable is used exactly once at runtime, and an unrestricted, which is the same behavior as Idris 1. We see the multiplicities of variables by inspecting holes. For example, if we have the following skeleton definition of append on vectors. Okay, well, let's try that. You can look at the whole append right-hand side. Okay, I'm trying not to block the chat, because if for some reason someone ever actually joins the chat, I won't be able to see it. It's highly doubtful that anyone will actually join. Let's try this out. I might have to import the vect type here. I'm going to explain vect in a moment. Oops. Why am I typing this out? I don't know, because it makes me feel better. I don't know. For me, I feel better typing things out than just copying and pasting them. I feel like it sticks in my mind better. That's the only reason why I'm not just like copying and pasting stuff from the page. I don't know. It's weird. If I'm typing stuff, I feel like I'm actually it feels like the stuff sticks in my head more, and I'm learning better. Good. Yes, English. So the vector type here is essentially a list. So you're probably familiar with lists, or like linked lists in other languages, where maybe in Java you have like a list of integers, right? You might specify it as like this, or I don't know what the syntax is in Java anymore, but I know in Rust it would look more like angle brackets. In Scala it's square brackets. Doesn't really matter. You'll notice that list is a type constructor because it's parameterized by some type. Usually, the generic version is type T, and then you instantiate it with different concrete types, right? Vector is similar. Vector is a list, but it has 2 parameters, and the first one is actually not a type. The second one is still a type, so you could use natural number here. In this case, n and a are just generic, so this is for any type a, and this is for any number n, and this is also for any number m. So spoilers, this is a natural number, but we wouldn't put nat here because that's a type. This actually is a value. So this is how you would describe a concrete instance of this like vector type, right? You pass in a number, and that number is actually the length of the list. So it's a list of nats of length 5. That's how you read vector. It's pretty simple. And the reason why we have the length here, if you're not aware, you can usually index into data types, right? Like let's say you have an array, right? A lot of programmers are familiar with arrays, right? You might have an array of type that contains natural numbers, but one of the things about arrays is that if you, I don't know, Oh, that's Scala syntax. What would I don't know. Whatever. We'll stick with the Scala syntax, or we'll just do like a let here. Pseudocode. So one of the things that you generally can do in all of these more mainstream languages is index into an array like this, right? So this gets like the, I don't know, fourth element of an array if you're a zero-based index, right? 0 is the first element, so 3 would be like the fourth one. But of course, that can lead to problems if there isn't, if A isn't actually 4 items long. So you might get an index out of bounds error in C or like C++. This might actually be a really big problem because you might run into memory safety problems there, right? So by knowing the length at compile time like this, you can actually have the compiler give you an error. Like the code won't compile at all if you try and do something like that, something that's obviously wrong and dumb. So the compiler can help you catch errors automatically, gives you instant feedback, and yeah, that's the main reason why you'd want to parameterize your lists by their length. And obviously, before I move on here, this is not something you can do in Java, right? Like, you can't just put a number into a type variable, right? Like, a value 5 is not a type, right? Like in Java, you can only have type parameters for stuff with these like angle brackets for generics. Generics always are for type variables, but because we have dependent types, we're allowed to use values, and so we have a lot more power at the type level here. In Idris, it's a very cool feature. Yeah, that's the basic rundown of how dependent types are being used, at least in this example. Types and values are kind of treated the same. They're both first class in the language, hence why this is possible. And yeah, this is essentially appending two vectors together, and you get back a vector that has length n plus m. And that's I feel like that's a pretty self-explanatory type signature. It's very easy to understand and gives you some very nice guarantees, because now you know that the vector that you get out of here is going to be a bit longer, right? You know it's going to be specifically of this length, n plus m. So anyway, what we were looking at here was the whole. They want us to inspect the whole, so I can do a \t. And I think I screwed up. Error while processing type of append. Undefined name vect. Okay. Yeah, we're going to have to import that. So import, I think it's data.vect. I don't remember. It's been a while since I've written Idris. There we go. Type checks. So now we can see, yeah, 0 for m, 0 for a, and 0 for n. The 0 next to m, a, and n mean that they are in scope, but there will be 0 occurrences at runtime. That is, it is guaranteed that they will be erased at runtime. Okay, it's good to know. Obviously, if stuff is erased at runtime, that's nice, because then, it means less overhead for a program, better performance generally. So that's good. Multiplicities can be explicitly written in function types as follows. So we have ignore. Okay. 0 for n. So this is called ignore n. This function cannot look at n at runtime. Alright. Duplicate. Okay. So x can be looked at exactly once, though, right? This function must use x exactly once. So good luck implementing it, by the way. There's no implementation because it would need to use x twice. Oh, yeah, because this is a tuple, right? So you'd have to... this returns a pair of values of type A, but we only have one value of type A, which is x, and we can only use that value once, so we will never be able to implement this. So if we could put a 2 here, then that would work. But I think if I'm reading all this stuff correctly, we won't be able to do that because that's just not allowed, right? Remember up above it said only 0, 1, or any, I think, unlimited is allowed. Hello? You wanna \A? No? What? Why is that not working? That should work. It might be a bug. Yeah, that's not doing anything. That's really weird. Okay. Wonder why that is. What if I remove the multiplicity? Does it like that now? Yeah. Okay. So that's an interesting caveat. I guess because I tried to use a 2 there, it didn't like it. If I put a 1 there instead, will it let me \A? Yes. Okay, so 2 is not valid. Yeah, so this will never be able to be implemented. No matter how hard you try, you cannot implement this function. So this code will never compile. Good to know. Okay. If there is no multiplicity annotation, the argument is unrestricted. If, on the other hand, a name is implicitly bound, like A in both examples above, the argument is erased, so the above types could also be written as so. Okay, so all my functions before didn't have any kind of a bound on them. Oh yeah, I forgot to mention, there's a syntax for naming your parameters in the type signature, which I totally glossed over entirely, but yeah, that's what this is doing. So if you exclude the 0 or the 1, if you exclude the multiplicity, essentially it's just saying you have a parameter of type nat named n. It's yeah, nothing special. I mean, if you've ever programmed in Java or any other programming language, you name parameters all the time. No big deal. So this curly brace syntax is for implicit arguments, so you don't have to explicitly pass this in when you're calling the function. That's nice. This underscore I think is just please infer the argument type for me, because it should be obvious from the context. If inference doesn't work, that means it wasn't obvious. A lot of people I know are kind of scared of type inference. They think it's like magic or something, but I mean, in general, inference just looks for something that's already obvious, right? Like if this wasn't possible to be determined, then it would just have to throw an error. Usually it kind of narrows it down to a single possibility, and then it plugs that in. So that's just doing type inference here. Okay, so they've rewritten this. Notice. Oh yeah, because A here is actually yeah, A is implicit, right? Like you don't actually have to define the type of A anywhere here. Obviously the type of A would be type, right? Because like I said, this one is a natural number, which is specified here, but this one is a type argument. This is like what kind of contents does this vector have? So the type that would have to be inferred here would just be type, or capital T type. I think the same thing would happen here probably. Yeah, right, because X has to have type A, so A obviously has to be a type. So if we were to write this out more explicitly, it would be duplicate 0A and then type blah blah blah, etc. Alright, so this section describes what this means for your Idris 2 programs in practice with several examples. Okay, that's great, because I was trying to figure out, how is this stuff actually used? Is this useful? Well, obviously linearity is, useful. We've seen how it's used in other languages, well, at least affinity, affine type systems. We've seen how those are used with languages like Rust, and Rust is obviously quite popular these days, so... Okay, so talking about erasure, how to know what is relevant at runtime, what is erased, linearity, using the type system to encode resource usage protocols, and then they're going to talk about pattern matching on types, which this surprises me because I don't really see how that has anything to do with multiplicities, so yeah, I'm kind of curious to know what we get into there. The most important of these for most programs, and the thing you'll need to know about if converting Idris 1 programs to work with Idris 2, is erasure. Good to know. So erasure is the most important part. The most interesting, however, is the thing which gives Idris 2 more expressivity, and that's linearity. Oh, alright. So this is the exciting stuff, but the most important thing to know is erasure. So we're starting with exciting. Yeah. The one multiplicity expresses that a variable must be used exactly once. By use we mean either if the variable is a data type or primitive value, it is pattern matched against. For example, by being the subject of a case statement, or a function argument that is pattern matched against, etc. Okay. Alright. So, right, there's a separate syntax. There's a lot of like alternate syntaxes for things in Idris. Kind of makes me go crazy sometimes. It's like, why do we have like different ways of doing the same thing? But yeah, essentially, I showed you this pattern matching syntax where we just, have multiple, essentially, definitions of the same function, but for different cases of the argument. There's another syntax that you can use. We'll call this one handle error 2. Let's see if I can get this right on the first try. I probably won't. Where we can say case x of, and then we can give the two cases here. I forgot to turn off my heater. Give me a moment. There we go. I always forget to do stuff like that. Yeah, so we can give parse error here, and we can give it an argument named error message. We'll pattern match, supply the HTTP response error case. You can see where I'm going with this. It's very, very similar to what I showed above. Actually, there's a shortcut for doing this case of thing. I don't remember the keyboard shortcut for it though. I think it might have been like \M. But yeah, essentially I could do the exact same thing as I just did above, but I can define it in a single function like this. Written error message, yeah, X is error, cool. So that's equivalent to the above, except it looks a little bit uglier, I think. There are some uses for this when you're, writing programs, and this is maybe a little bit more convenient. But otherwise, these two things do the same. They do the same sort of thing. So yeah, that's a brief detour about case of. So that's what they mean when they're talking about case statements here. If the variable is a function, then the function is applied. Ran with an argument. Okay. Interesting. Good to know. Good to know. Let's see how this works on some small examples of functions and data types. Let's see how it can be used to encode resource protocols. Whatever that means. Okay, so they have a page on resource protocols, it seems. I don't want to jump to that just yet. Actually, I think that's part of this page. If you look at the URL at the bottom left there, it says, yeah, multiplicities.html # resource protocols. So that's probably later. Above, we saw the type of duplicate. Let's write it interactively and see what goes wrong. We'll start by giving the type and a skeleton definition with a hole. Yeah, I already went through that rigmarole. Checking the type of the hole tells us the multiplicity of each variable in scope. If we check the type of this hole named help, we'll see that we can't use A at runtime, and we have to use X exactly once. Alright, if we use X for one part of the pair, then the type of the remaining hole tells us we can't use it for the other. Oh yeah, look, you see that x's multiplicity went down by 1. So it started at 1, now it's 0 after you do that. You know what, let's try that. That actually looks fun. Let's try this. Just gonna paste that in. I'm gonna do a little type check. Error when processing right hand side of duplicate. Try to use linear name x in nonlinear context. What? What? How come I don't get that? I don't get what they're... Uh-oh. That's not good. That's weird. What if I type it out myself? Is this like a Windows issue? I mean, I'm in the Linux subsystem. It shouldn't be. That's super weird. Alright, we saw this. Okay, can I type check this? Yes, I can type check that. What am I doing? I wanted to CW. I'm gonna try partially applying this thing. Trying to use linear name x in a non-linear context. That's weird. I think their docs might be outdated. This seems a little bit strange. I don't really know why that would be. Okay, so that's a pitfall. Oops, the documentation isn't quite accurate to what I'm seeing. Yeah, that's really weird. But that works. Man, I wanted to see this. I wanted to see this thing decrease. Alright, well, the same thing happens if we try to find duplicate x. Alright, well, let's try the other one. See if that is any better. Probably isn't. Nope! It is not better at all. Not in the slightest. Okay, that's fine. To avoid parsing ambiguities, if you use an explicit multiplicity for a variable, as with the argument to duplicate, you need to give it a name too. Okay, but if the name isn't used in the scope of the type, you can use underscore instead of a name as follows. Sorry, my brain like completely did not parse that at all. You give an explicit multiplicity for a variable, as with the argument to duplicate. Okay, yeah, an explicit multiplicity, like 1. You need to give it a name. But if the name isn't used in the scope of the type, you can use underscore. Okay, let's try that. Oops, what am I doing? Of course that doesn't help. Cool. Does this actually type check? Imagine if this type checked. Yeah, no, okay, that doesn't work. Okay, what if I give it a name x? Undefined name x. This is really weird. This is really, really weird. Now, I did pull this version of the compiler fairly recently from the repo, so this might be like a broken build or something, I don't know. So that might be the reason why this doesn't work. That'd be very unfortunate if that was the case. But it seems to, like, the rules seem to be correct, right? Like, this should type check. Actually, it doesn't. What? Really? Undefined named x. Okay, but can I can type check this though? Okay, yeah, no, the file itself type checks. That's really interesting. But if I put a 1 here, that doesn't type check anymore, right? If I type check handle error, yeah, now it's Trying to use a linear name x in a non-linear context. Dun-na. So it feels like the compiler is a little bit smarter now, maybe. Like it immediately knows that this is going to fail. Before it even scans the whole and tells me the information about everything. Right, like it already knows that I can't use x twice here, and x is the only thing I have. So maybe the Idris compiler is trying to be smart. I don't know. It's weird. The intuition behind Multiplicity One is that if we have a function with a type of the following form, f k, so it uses x exactly once, x is type A, return a B. Then the guarantee given by the type system is that if f applied to x is used exactly once, then x is used exactly once. So if we insist on trying to define duplicate, it just will complain. Yeah, this error message is different. It doesn't even say that there are two uses of linear name x for me. It's interesting. A similar intuition applies for data types. Consider the following types: lin, which wraps an argument that must be used once, and unner, which wraps an argument with unrestricted use. Okay, so that means unrestricted, and that means linear. Okay, so lin takes a type, returns a type. So it's like list, right? List takes a type and returns a type. Just want to show people so they don't get confused. Like, you know, in Java you give list int, right? So so list takes the type integer and returns the type list integer, right? List itself is not a type. This is not a type. This is a type constructor. It takes a type and then it returns a type. So that's essentially what this type signature type to type is saying. Anyway. We've got lin. Takes one. Okay. Unrestricted. Okay, I'm not really sure what this is used for. If make lin is used once, then x is used once. But if make unrestricted x is used once, there's no guarantee on how often x is used. We can see this a bit more clearly by starting to write projection functions for lin and unrestricted to extract the argument. Okay, that is kind of annoying. These Windows error sounds. I wonder if there's a way to disable that, because it's kind of bothersome. I'm not sure how they're showing up on the stream. I'm not sure if like they're super loud or if they're not being heard at all. I imagine they have to be heard though, because I'm pretty sure I'm recording my desktop audio in general. So cool. I autopiloted into just manually typing this thing out. That's cool. Doesn't matter. We got there anyway. So get lin. How many lin? Check the holes. Undefined name. How many lin? Okay, this seems broken. Oh, right, because I didn't define the type. Let's define the types. There we go. So now, this should type check, hopefully. Oh wait, I still have that duplicate. Let's get rid of you. Alright. My output matches exactly with theirs. Checking the types of the holes shows that for getLin we must use x exactly once, because the val argument is used once by pattern matching on it as makeLin x. val argument. I guess since they gave it an implicit name, I guess the name that they're talking about is val? The val argument is used once by pattern matching on it as, yeah. So this, I guess, name would have been val. And by pattern matching on val as this make-lin thing, yeah. If make-lin is x is used once, x must be used once. Okay. I feel like they're trying to teach me something and I'm not understanding exactly what I'm supposed to get out of this. I think what they're trying to say is that make-lin is like a record type, or like a struct, essentially, that holds... Well, not make-lin, but make-lin is the constructor for lin, and essentially it's kind of like a struct that holds a single value of type A, but that value can only be used exactly once. So let me demonstrate that exactly here. It's sort of like if I had like a struct lin, right? Just going with a more Rust syntax here. And we had a variable of type A. So that could be any type A. You can't do this in Rust because you'd have to actually put the type parameter there, but anyway. And that variable will be called, I think, val, probably. And then you had like a constructor that was called like make-lin out here that returned lin. Yeah, that's essentially what this is. It's just like a struct of like some value of type A, but it can only be used once. Pseudo syntax, etc. Okay, so what do we get here? Forget unrestricted. However, we still have to use val once. Again, my pattern matching on it by using, but using make unrestricted once doesn't place any restrictions on x. So x is unrestricted in the body of that. Okay, so let's try get under. Oh god, Windows, please. Okay. Whoops. Yeah, that is super annoying. Let me see if I can do something about that next time. Okay, and that matches pretty much what we expect. If get_lin has an unrestricted argument. Oh, okay, so again, every time I hit escape in Vim and I'm already in this normal mode, it makes that noise. It's really bothersome. Alright, so we're going to do that. And wait, no. That's interesting. I wonder if this type checks. It still does. Okay, so you can do an underscore for the name there. I don't think it really matters. Like, we could probably get rid of it entirely, like in their example, but you can do that, apparently. Then x is unrestricted in how many lin? Remember the intuition from the type of make_lin that is that if make_lin x is used exactly once, x is used exactly once. But we didn't say that make_lin x would be used exactly once, so there's no restriction on x. What? So if I change this to x, does that type check? Oh, it does. Oh. That is interesting. Okay, well that makes sense, I think. From the type of makelin is that if makelin x is used exactly once, x is used exactly once. But we didn't say that makelin x would be used exactly once, so there's no restriction on x. Right. Because we didn't put a restriction on this, we can use x as many times as we want? Is that what I'm reading? Well, now I have to test this. Alright. Do type check. Actually, let me write first before I try to do that. That does type check. So I can use x as many times as I want, despite the fact that we specified in the type definition for that constructor that the argument has to be used once. Okay, interesting. Alright, that is very, very, very interesting. So this is just saying if makelin is used exactly once. So if we had a restriction on this, then x has to be used exactly once. But if it's not restricted in any way, then you can use it unrestricted. That's really weird. I feel like there's something else I have to try here then. Let me think about that a little bit. How long do I want to go today? Maybe 4:30, I guess, is when I want to stop. We'll see. So, if that's the case... Oh, that's really weird. Hold on. Okay, let me try something. I've got an idea. Oops, I just pressed the wrong key. 1. We'll do this again. Okay. So this shouldn't work, right? Like, if I do this, this is going to not type check. Yes. Okay, but if I do the exact same thing over here, this will type check. Watch, watch. This is gonna type check. Oops. No. No, it doesn't. I don't understand anything at all. What? Then this is exactly the same, isn't it? So do multiplicities just not affect things when they're stuck into constructors? Is that what I'm reading? Because that's weird. That this... Like, both of these will type check. Yeah. That's super weird. Okay. I guess I can ignore multiplicities in constructors then? I mean, that's not what they say, though, explicitly, but that's my intuition from this. Because I would have thought that if I restricted this, because it's still unrestricted on the argument, it doesn't matter. That is interesting. Alright, we'll look at this more later. I want to move on. Try and understand this a little bit better in the future. But I think I kind of have a vague understanding of how this works so far. I'm sure I'll build more of an intuition as we go through. So resource protocols. One way to take advantage of being able to express linear usage of an argument is in defining resource usage protocols, where we can use linearity to ensure that any unique external resource has only one instance. And we can use functions which are linear in their arguments to represent state transitions on that resource. A door, for example, can be in one of two states, open or closed, okay? So now we're moving on to doors. I'm just going to clear this stuff. Well, we can leave it. It doesn't really matter. Type checks, whatever. Data door state equals open or closed. Okay, and we have data door. Takes a door state, turns a type. Okay, this is interesting. Make door is the name of our constructor. The door ID, which is an integer. Okay, not a natural number, that's an integer. So probably 32 bits. Door with a state st. So notice that they don't actually explicitly mention taking a door state variable called st anywhere. So my imagination says that it's probably going to be something like this door state that's implicit in here. I'm guessing that's what that's doing, because the signature for the data type itself says it takes a door state and returns a type. So that's kind of weird. I'm guessing that's what it's doing. Yeah, if you're wondering, that means we can define a function like this, where the type of bar is door, but remember, door needs to take a door state, so we have to give it open before that's considered a type. So it's kind of like what we were doing with lists, right? Where we take a type and then we return a type. In this case, we take a value of type door state and return a type. So this is just more dependent type magic. Really cool stuff. We'll just back out of that for a moment. Thanks Windows for making weird noises again. Okay, we're just pretending here. Imagine the door ID is a reference to an external resource. We can define functions for opening and closing the door, which explicitly describe how they change the state of a door and that they are linear in the door. Okay, so we can define open door. So it takes a door, a closed door, can be used exactly once, and it gives us an open door. Okay, yeah, that makes sense, right? Like if we have a closed door, we want to be able to transition to an open door. We can't have a closed, the door is no longer closed anymore, right? Like that's a state transition. We also have closed door, which looks similar. Notice that there are actually preconditions here, right? Like this door that we pass into open door has to be closed. We cannot pass an already open door to open door. And same with closed door. We cannot pass an already closed door to closed door. So you can only call closed door on an open door. Otherwise the program doesn't compile. And of course, yeah, our post condition here is that the door that we get back out is open when we open it, and the door we get back out when we close it is going to be closed when we close it. Remember, the intuition is that if open door D is used exactly once, then D is used exactly once. So provided that a door D has a multiplicity of 1 when it's created, we know that once we call open door on it, we won't be able to use D again. So that door is gone. Given that D is an external resource and open door has changed its, this is the wrong form of its, changed its state, this is a good thing. We can ensure that any door we create has multiplicity 1 by creating them with a new door function with the following type. Okay, so this is interesting. So you can create doors with particular multiplicities. I should probably type check that stuff just to be sure. Oops. oops, yeah, what is going on here? We have, oh, this is confusing. This is very confusing. Look at this signature. Okay, what is going on here? Okay, so P is a function. This is a function type. So this is a lambda. P is a lambda, and that lambda's type is a function that takes a closed door and returns an IO unit. So new door is a function that takes a lambda and then returns IO unit. Hopefully that's clear. Undefined name close, because I wanted closed. There we go. Good to check these things. That should compile. Yep, it sure does. Cool. Okay. I think I scrolled down too far. That is new door takes a function, which it runs exactly once. That function takes a door, which is used exactly once. We'll run it in IO to suggest that there is some interaction with the outside world going on when we create the door. Since the multiplicity 1 means the door has to be used exactly once, we need to be able to delete the door when we're finished. So we have a delete door. So I think it's kind of obvious what kind of analogies you could make here with this, right? Like, obviously they're talking about doors, but you could easily replace door with file, right? File state open or closed. The file needs to be opened. If it's already opened, you don't need to open it again. The file needs to be closed at the end, right? You call close file. So this is I mean, it's an interesting example, but it could have easily been made into something that sounds a lot more practical just by changing the word door into file. I think, right? I think that's pretty obvious from this example, but yeah, just in case you haven't made that connection yet. Delete door. Right, I was defining delete door. I got distracted because that's what I do. Closed to IO unit. So an example correct door protocol usage would be door prog. Oh, look at this thing. We're getting into the weeds of Idris syntax here, I think, but bear with me. I've already explained some of this stuff, so it shouldn't be too bad. I can do this. Yeah, doesn't take any arguments. Okay, so they move the equals to the next line. Oops, don't press D. Don't want to delete anything. So they call new door. Right, so this takes a lambda, well, more specifically a function, because technically we could pass in a named function into new door. It doesn't have to be anonymous. So just to be pedantic about this. All right, so we call new door and we're passing in a lambda here. So D is a door. It's a closed door specifically, right? If you look at new door, they take a closed door in this lambda. We're going to call open door on that closed door. And we're going to get D prime. Now D prime is going to be an open door because that's what open door returns. We have D double prime, which is defined as closed door D prime. Okay, so we have a closed door, right? Now we open it. and then we close it again. So that's what this program is doing. And then after we've closed the door, we just delete the door. Yeah, because this is functional programming, right? We're not actually mutating our door D, probably, I imagine. Actually, we might be, because it is doing I/O, right? Like, no, new door is doing I/O. Open door and closed door are just returning doors, so it's probably just returning a completely new door. Hence, D prime, D double prime. Well, although everything is linear in this context, so I guess you could mutate it in place and it wouldn't actually be a problem. That's interesting to think about. Anyway, let's see what they have to say about this. It's instructive to build this program interactively with holes along the way and see how the multiplicities of D and D prime change. For example... Oh, okay. I'm just going to comment this out because I don't want to retype or copy and paste again. So we're just going to do this. Error. The undefined name what now? Oh, because I forgot the in. I need the in. There we go. What's nice about Idris's interactive keyboard shortcuts is that it automatically saves your file before it runs them. So if you forget to save your file by doing like a :W, then yeah, pressing \T will still get you the type of the updated code, which is cool. It's helpful. So door closed can be used 0 times. Yeah, D can be used 0 times, right? Because we opened it, right? We passed it into open door, so that took ownership of our door, right? So now we can no longer use it, and then it gave us this new door that can be used exactly once. You see the analogies with Rust here. Note that the 0 multiplicity for D means that we can still talk about it. In particular, we can still reason about it in types, but we can't use it again in a relevant position in the rest of the program, whatever it means by relevant position. It's also fine to shadow the name D throughout. Oh, okay, so they have variable shadowing here in Idris. That's interesting. Variable shadowing is one of those features that I've never really understood, like, why it exists, but I know Rust has it. Apparently it's a holdover from, like, Lisp or something like that. I don't know. That's what someone told me. I don't actually know if that's true, but yeah, it's one of those features that's very controversial, and I know a lot of people are like, oh, variable shadowing evil, variable shadowing bad, and there's also people who seem to like it. So yeah, I don't know. I don't really know how harmful variable shadowing is. So yeah, I don't really have a strong opinion on it either way. But it is interesting that Idris does support this kind of variable shadowing. If we don't follow the protocol correctly, create the door, open it, close it, then delete it, then the program doesn't type check. For example, we can try not to delete the door before finishing. Ooh, hello. That sounds fun. Okay, let's close the door. Alright, we gotta get rid of that in. Remember? That's extra. Ah, my ears. Don't do that, Windows. Now we're going to print. We're going to print. What could possibly go wrong? Posably, yes. Good, good. Alright, now we're going to do some type checking. God, Windows. What is this? Oh, right, it's supposed to return an error. 0 uses of linear name D double prime. So we didn't close it. Oh no! I mean, we didn't delete it. Right? So you can see that this would be incredibly useful for making sure that file handles are properly disposed of. This is definitely really cool. I like this. This is very, very cool. This can prevent resource leakage. Definitely would be nice to have. And it's cool that Idris has this. Definitely really liking that. There's a lot more to be said about the details here, but this shows at a high level how we can use linearity to capture resource usage protocols at the type level. If we have an external resource which is guaranteed to be used linearly, like door, we don't need to run operations on that resource in an I/O monad, since we're already enforcing and ordering on operations and don't have access to any out-of-date resource states. This is similar to the way interactive programs work in the clean programming language, and in fact is how I/O is implemented internally in Idris 2 with a special %world type for representing the state of the outside world that is always used linearly. Okay, that's pretty cool. So yeah, I think that covers the really cool parts of linear types for the most part here. We've got one final example here, it looks like. Public export data IO res. Okay, it's a type constructor, right? Type to type, just like a list or an array. Make IO res result. Okay, this is just kind of showing internally how this is used. Takes a world. Returns an IO res. IO is defined like so. Okay, make IO. As a linear function, it takes a world and returns an IO res. So this is like new door, right? It's a function that takes another function as an argument and returns IOA. Having multiplicities in the type system raises several interesting questions, such as, can we use linearity information to inform memory management and, for example, have type level guarantees about functions which will not perform garbage collection? So this is like what Rust does, right? Rust uses its affine type system to avoid garbage collection. That's why Rust doesn't generally have a garbage collector unless you're doing reference counting with like RC or ARC. How should multiplicities be incorporated into interfaces such as functor, applicative, and monad? If we have 0 and 1 as multiplicities, why stop there? Why not have 2, 3, and more, like granule? Okay, I don't know what granule is, but it's a different language, it looks like. What about multiplicity polymorphism, as in the linear Haskell proposal? Even without all of that, what can we do now? Yeah, I think that this is these are all open questions. This is very interesting stuff. Yeah, definitely interesting to see how multiplicities are going to be incorporated into interfaces and interface methods. And I was wondering, yeah, why can't I specify 2? I guess more importantly, we should be asking ourselves, is it useful to be able to specify like something can be used exactly 2 times or exactly 3 times, right? Is there a business use case for that? And right now, I guess Idris feels there isn't a business case for that, hence why it doesn't support those, right? Like we just have unrestricted 0 or 1, and those are the ones that seem to come most commonly. I mean, Rust is getting by just fine with affine types, which means a variable can be used either 0 or 1 times. So that's an interesting question. Like, do we care about 2 and 3 and other types of multiplicities here? Multiplicity polymorphism, that sounds interesting. Not really sure what they mean by this. Obviously, I haven't looked at the linear Haskell proposal, so I don't actually know where that's headed. But this sounds more like being able to abstract and generalize over multiplicities as a feature. These functional programming languages are all about abstractions and generalizations, so that doesn't surprise me that people would be looking in that direction and trying to evaluate how useful that is. And yeah, definitely the most interesting question of all is, even without all these things, what can we do currently with just 0, 1, and unrestricted? Like, is 0, 1, and unrestricted enough? Do we need more than that to do useful things in programming? So that's really cool. I definitely like that they have these open questions here. All right. So now I guess we can move on to Erasure. Let's see if we can go through this quickly. I don't know if I want to stream for that much longer. So let's take a quick look at Erasure. So we covered the really interesting and cool stuff, right? We now know of ways that we could like perhaps enforce at compile time that a file handle is closed, right? Like that's cool. You know, you can't do that in Java. You know, I mean, you can try and finally all you like, but there's no compiler guarantee anywhere that says, hey, you know, if you you didn't close this file, it's easy to forget these kinds of things, unless you're, you know, super aggressive about, oh, if I open a file, I better like try and finally that right away kind of thing. Yeah. Let's take a look at Erasure here. The one multiplicity give... What? The one multiplicity gives... There's an S missing. Us many possibilities in the kinds of properties we can express. But the zero multiplicity is perhaps more important, in that it allows us to be precise about which values are relevant at runtime, and which are compile time only, that is, which are erased. Using the zero multiplicity means a function's type now tells us exactly what it needs at runtime. Alright, let's take a look at this. For example, in Idris 1, you could get the length of a vector as follows. Okay, so this is just taking a vector, returns a natural number, blah, blah, blah. This is an implicit argument made explicit. So it calls into scope n here, and it just returns n, which makes sense. That's just the length of the vector. That's fine since it runs in constant time, but the trade-off is that n has to be available at runtime. So at runtime, we always need the length of the vector to be available if we ever call vlen. Idris 1 can infer whether the length is needed, but there's no easy way for a programmer to be sure. In Idris 2, we need to state explicitly that n is needed at runtime. Okay, so here they actually, specify that n is an implicit argument in the type signature here, and then they just use n without ever like summoning it in here. Oh yeah, right. I think that's actually a syntactic change in Idris 2. Yeah, so this is valid Idris 1 code. If you tried to do this in Idris 2, it would fail. I'm pretty darn sure. Actually, you know what? Let's test that out. Why not? We have an environment for testing. Let's just do it. Alright, doorprog can go away. Let's paste. Alright, that shouldn't type check, right? Yeah, look at that. So the way that it has to work now is you put n here. So subtle differences between Idris 1 and 2. Kind of interesting. We'll type check again. And it works. Cool. Incidentally, also note that in Idris 2, names bound in types are also available in the definition without explicitly rebinding them. Yeah. In fact, if you try to explicitly rebind them, I'm pretty sure it actually fails. We can test that, right? We can test that. Let's do that. If I rebind it, does it matter? Nope. Okay, never mind. It does work. So you can explicitly rebind it, but Idris 2 allows you to get away without having to do that. So that's nice. This also means that when you call vlen, you need the length available. For example, this will give an error, some lengths. M is not accessible in this context, right? Because you'd have to do the implicit arguments. You have to tack those on at the beginning. Let's try that one. Some lengths. The vector of M A vector and A returns a natural number. X's and Y's. We try to get the length of X's and add the length of Y's. This won't type check, right? No. But if we specify that m and n are both natural numbers, by the way, this is a cute little shortcut you can do. You can just put a comma in between variables that have the same type, and it's just a little shortcut. And it type checks. Yay, we did it. Needs to use m as an argument to pass to vlen x's, where it needs to be available at runtime. But m is not available in some lengths because of multiplicity 0. We can see this more clearly by replacing the right-hand side of some lengths with a hole. Ooh, okay. Let's do that. Let's delete this first. Alright. I want to... some lengths RHS. Check the type of that bad boy. Yeah, it says n and m are both used 0 times. Instead, we need to give bindings for m and n with unrestricted multiplicity. Oh wow, they just infer the type. Look at that. They just infer the type. Yeah, so that's the same as what I did earlier, except instead of actually explicitly saying these are natural numbers, they decided that it'd be faster to just put an underscore there. Let the compiler figure out that has to be those have to be natural numbers, and you know they have to be natural numbers because vector's first argument is a nat, right? Like that's obvious. There's no magic here. A lot of people get scared of stuff like this, but it's not magic. Remember that giving no multiplicity on the binder, as with m and n here, means that the variable has unrestricted usage, blah blah blah. If you're converting Idris 1 programs to work with Idris 2, is probably the biggest thing that you need to think about. It's important to note, though, that if you have bound implicits, such as exciting fun t, then it's a good idea to make sure that t really is needed, or performance might suffer due to the runtime billing the instance of t unnecessarily. Ooh. Right, because if you explicitly specify or explicitly bind an implicit argument, right? So this t is probably a type argument, I would imagine. Like, imagine coffee and moonbase are kind of like list or array. They take a type and return a type. So in this case, so in general, types are things that only exist at compile time, right? You don't really need types at runtime. I mean, excluding reflection, of course, but you know those types are a little bit different. Those are usually considered to be like tags. There's a bit of a distinction there, but because types are not needed at compile time, you pretty much always want to give them multiplicity 0. But in this case, because we've explicitly bound t by specifying it here, by not just leaving it out of the type signature, then this will be unrestricted instead of 0, and so it'll exist at runtime, I think. I think that's what that's saying. So, yeah, I guess types can exist at runtime in Idris too. Not really sure how that works. That's interesting. Maybe you can use that for, like, reflection. I'm not sure. But usually most people that I've talked to consider them to be kind of, like, separate things. Like, type tags are, you know, their own thing. So it's a good idea to make sure t really is needed or performance might suffer due to the runtime billing instance of t unnecessarily. One final note on Erasure: it is an error to try to pattern match on an argument with multiplicity 0. Right, like they said earlier, if you when you pattern match on an argument, that counts as a usage of it, unless its value is inferable from elsewhere. So the following definition is rejected. Yeah. The following, however, is fine because in S0, even though we appear to match on the erase argument x, its value is uniquely inferable from the type of the second argument. Okay, so they've created something called S-bool with two constructors, S-false and S-true. Okay, we have S0. Okay, this takes a bool with a multiplicity of 0. Interesting. And they take an S-bool of X, right? Uh-huh. So this is being used 0 times, even though we're pattern matching on it. It's fine to give this a multiplicity of 0 because that's information that will be erased at compile time. Because this boolean isn't actually being used in like the function body, right? It's only being used to as like a parameter for this S-bool type. So that's interesting. You'll notice that you can't have a case of true and S false, right? Like if they tried to add that here, it wouldn't compile. In fact, I can prove that to you right now by making Windows make funny noises. Yes. No. Ah, I'm just trying to go up, please. Oh, it swallowed up some of that stuff. Okay, weird. I can just do that. There we go. That should compile. Okay, cool. And with that, I can prove that we can't have an S true with false, for example. Like that's not something that can happen. That's gonna explode. Yep. So it's just smart enough to realize that this case can't happen, so we don't actually have to specify it. We don't even have to say like this is impossible or anything like that. Like that's not necessary. Yeah, cool stuff. Experience with Idris 2 so far suggests that most of the time, as long as you're using unbound implicits in your Idris 1 program, so basically as long as you don't actually explicitly write out your implicit type arguments in your type signatures. So if I got rid of this, that's an unbound implicit for n, right? N is implicitly defined, but it's not bound. Now it's bound. Right. What were they saying? Yeah, most of the time, as long as you're using unbound implicits in your Idris 1 programs, they will work without much modification in Idris 2. The Idris 2 type checker will point out where you require an unbound implicit argument at runtime. Okay, that's nice. Sometimes this is both surprising and enlightening. Good to know. That's helpful. I'm glad that the compiler actually points it out. Like, hey, you actually need this information available at runtime. Otherwise, I can't do anything here. That can help you reevaluate your design and implementation of it. Alright, I'm a little bit over time, but I don't really have like a strict or hard deadline here, so I'm just going to try and wrap this up because this looks really short. So we've got pattern matching on types. One way to think about dependent types is to think of them as first-class objects in the language, and that they can be assigned to variables, passed around, and returned from functions just like any other construct. But if they're truly first-class, we should be able to pattern match on them too. Idris 2 allows us to do this. Yeah, so this is a feature that I think was missing from Idris 1. You couldn't actually pattern match on types themselves. And so Idris 2 allows you to do something like this. So here's a wildcard. It's kind of like a default case, right? If you're coming from Java, you have like switch statements with a default case. That's what the underscore does. It caches everything else. But you can take a type now, it looks like, as an argument. And you can pattern match on it. So you can check if the type is an int type, return the string int. If you get a list of any type A, then yeah, you can. Okay, so they have a special show type function for type. So notice how earlier when I was writing the error stuff, actually I might even still have it here. Show, yeah, remember how I used the show function to convert this response code, which was a natural number, into a string? So it looks like for types, you can't just call show on a type and get a string representation of a type. You have to call a special show type function, and that'll take a type and convert it into a string. So that's interesting that they actually have a separate function for that. I wonder why that is. Oh wait, no, this is just recursive. Sorry, I'm oh wow, wow, okay. I managed to logic my way into something dumb. No, this actually is just a recursive call to show type. Okay, never mind. Forget what I was saying. We can try this as follows. Show type int. Yeah. Okay. Pattern matching on function types is interesting because the return type may depend on the input value. For example, let's add a case to show type. So the return type may depend on the input value. Okay, that's weird. Let's try this. Let's do some weird things. Something else. What else we got here? Show type. Nat to A. Now, I should probably put this case after, because, yeah, otherwise I'll catch it early, I think. Actually, I'm not sure about that, but I'm almost certain that that will prioritize the higher one in the list. Okay. The return type may depend on the input value. Oh, yeah, right. Wait. I'm confused. So help is a string. Yeah, well, because show type's return type is string. So return type A depends on the input value of type nat. Okay. Oh, right. So if we pass in 0, we could return nat as the type. If we pass in 1, we could return bool. If we pass in 2, we could return int. If we pass in 3, we could return string, right? So the return, the type of A depends on the value nat that's passed in here. That's interesting. So there's probably no real easy way to implement this, is there? Or we could call it recursively. That's probably what they're doing here, right? Function from nat to, and then they show type A and Z. Okay, so Z, like I showed earlier, is just 0 in natural numbers. You can also write it out as just the number 0, the numeral. But yeah, A appears to be a function because this is like function application syntax. A applied to Z. That's weird. How are they able to do that? Because A is not a function. I'm very, very confused. Shouldn't like this be bound to like a name? And then that like I'm really confused by that. That's weird. Function from nat to show type. Does that compile? I want to say that shouldn't. What? It does. What? Is this A here not the same A as this one here? What if I call this B? Is that'll complain, right? It does. Okay, I don't understand. Why is it A? Why A? Okay. Show type returns a string, right? And the argument to show type should be a type. This guy is a function that takes a natural number and returns a value of some type A, right? Or no, wait. We inspected the whole. A is a function from nat to type. Oh, okay. So because A is a function from nat to type, yeah, you can apply it to Z, which is a natural number. Then you get a type back, and then you can call show type on that type. Okay. How does it infer that this is a nat to type for A? That's what I'm curious about. How does it know that A has to be nat to type? Let's try inspecting. Dang it. See, I want to inspect A here, but it won't let me. Yeah. What? Okay, what if I comment this out and I put a hole here and I check that? Yeah, A is a type here. So specifically in this case, A is a function from a natural number to a type. That is weird. I don't know how it determines that. Like, why does that have... Why is it that A has to be exactly that? Why does A have to be a function from a natural number to a type? I don't think I understand. Like, list is a type constructor. It takes a type, right? It takes A, which is a type, and then it returns a type. So then we can pattern match, and yeah, that makes sense. Arrow is a type constructor that takes a type. It takes two types. It takes it's taking nat as its first argument, and it takes A as the second argument. So I would have expected A to be a type, not a function from nat to type. But although the nat to type is a type, right? It is applied fully to nat and type. It's just that I thought A would be type. I didn't think that A would be a nat to type. So that's confusing for me. I don't know. I'll have to think about that a little bit more. I want to move on. Alright. Note the multiplicities on the binders and the ability to pattern match on non-erased types mean that the following two types are distinct. Okay, so here's where multiplicities come in. Multiplicities on the binders. And the ability to pattern match on non-erased types mean that the following two types are distinct. Okay, so this is the identity function, right? There's no... A is not bound. Which means that it probably has multiplicity 0, but this one's not the identity function, or it's not the same as this ID function at least, because we explicitly bind the implicit argument A, and this means that it has unrestricted usage. I think that's one of the core lessons that they've been trying to teach us all along here. Like, this exists at runtime. Like, A definitely exists at runtime here, unrestricted. Here, A may not exist. It probably doesn't exist. It probably is given an actual multiplicity of 0. And actually, can I test that? Let's do that real quick. A. Yeah, C has a multiplicity of 0, so it can't exist at runtime. And that's just the type argument a, right? We can actually use x. X is fine. That'll still type check. I can prove that. Yeah. Because x is a value of type a. It's just that a itself, the type, cannot be used at runtime. Which is why in the not ID case, yeah, that's a strictly worse implementation of identity. Or, well, it's not exactly the same as this identity function because, yeah, this exists at runtime. In the case of not ID, we can match on A and get a function which is certainly not the identity function. Oh, so you can actually do more with that. Ooh, let's check that out. So we have this, A has a type. We'll do this. We'll do that. The usual. Okay. And they have another case here. So here they're doing explicit binding. A has value int. Oh god. Stop. Oh, I'm pressing the wrong key, that's why. Duh. Hand is not where I thought it was. Yeah. A equals int. Return some value, I guess. And in this case, you can return a different value. Oh, yeah, because we know that a is an integer. Yeah, in this case, we actually know that the type of this thing is an integer, so we could return x plus 1. But in this case, we don't know anything about the type of x, so we would just have to return x. Oh, that's actually really interesting. So this is not an identity function at all. Yeah, and they even okay, let's do this. Not ID 93. We get 90. I didn't get 94. What? Why didn't I get 94? I think I broke it. I think I broke it. That's weird. It didn't give me 94 like it was supposed to. Oh, wait. I know. Let me do that again. Ah. Not ID 93 gives us 93. Not ID the 93 or oops. Ah. The int 93. 94. There we go. The function takes a type as its first argument and then a value as a second argument, and essentially just, you know, tries to cast it as the type that's passed in. Tries to cast the value as that because, well, I don't think it's actually like an actual cast. It's just because 93 as a literal will automatically be inferred as a natural number. If you want the compiler to not infer it as a natural number, then you need to use this the int thing. So yeah, okay, there's a case where the compiler is maybe doing a little bit of more magical inference, I guess. So yeah, maybe that is kind of justified, but yeah, I don't know. Whatever. In this case, you can be explicit by using the, and you can say that the literal is an integer literal by, you know, passing in int. So that's really interesting. This is not actually an identity function. And you can actually use the types at runtime, huh? That is fascinating. And of course, this is all entirely type safe still because it's Idris. It's not like you're doing reflection and you're absolutely destroying all your guarantees like you would in Java. This is still Idris. It's still all type safe. That's really interesting. I'm trying to think like what that could mean. Like if you're writing like, I don't know, a database connector or something, like, yeah, now you'd actually have like, You could actually like use the types. You could like actually pattern match on like on the actual like types. I don't know. Maybe this could have some usage there. Because I know sometimes people will just use like reflection for handling like SQL types and turning them into like proper domain values. I don't know. That might be a little bit hacky though. I'm not really sure. That's really weird. That's really weird. There's an important consequence of being able to distinguish between relevant and irrelevant type arguments, which is that a function is only parametric in A if A has multiplicity 0. Right, because parametric polymorphism, yeah, we lose the guarantees if we do stuff like this, right? Like, this is no longer an identity function. We can't just trust that the only way to implement this function is to return the value that was passed in, because now we can actually pattern match on the type and we can do nasty, dirty, terrible things. So this is a function that I can trust to be parametric, and when I pass in an argument, it'll definitely return exactly that argument. But this one, I cannot trust it. So yeah, very, very important to pay attention to that, because that could lead to very interesting little bugs. And yeah, in the case of not ID, A is not a parameter, and so we cannot draw we can't draw any conclusions about the way the function will behave because it is polymorphic. Because the type tells us, okay, I don't know, this English here is really weird. It's really weird, and I think it might actually be wrong. Because the type tells us it might pattern match on A. Yeah. That's basically what I said. We can't trust this not ID function. On the other hand, it is merely a coincidence that in non-dependently typed languages, types are irrelevant and get erased. Then values are relevant and remain at runtime. Yeah, okay, yeah. Idris 2 being based on QTT allows us to make the distinction between relevant and irrelevant arguments precise. So types can be relevant at runtime outside of just, like doing reflection stuff, right? Like, that's interesting. Types can be relevant. Values, such as the n index to vectors, can be irrelevant. Yeah, because when you parameterize your vector by a value, like its length, you don't actually need that information at runtime. You can encode that entirely at the type level at compile time, and it's completely irrelevant to the runtime. So yeah, you don't have to keep that around. No extra overhead for that. All right. Well, that was a really, really cool tutorial on multiplicities. I enjoyed that. I enjoyed learning about that. It seems like there's more. This might be like a deeper dive. Let's look at this very quickly. Oh, this looks like it's a paper. I don't think I'm going to be reading that. I think I got everything I wanted out of this. This seems really cool. I can already think of several applications for this stuff, like pattern matching on types. That's interesting. It seems very powerful. It seems like this subtle difference between ID and not ID is something that's very important to know about, because that's the difference between, writing code that is buggy and writing code that isn't buggy. Like, you can trust this function, but you definitely cannot trust this one to behave the same as an identity function. And yeah, that distinction is super duper important to know, because your guarantees are completely different in these two different cases. I feel like stuff like this is, it's one of those kinds of things where it's like, oh, whoops, foot gun, didn't realize that, this is completely different from this. Definitely something that should be featured more prominently in their documentation, I would think, because that sounds very important. Because it's very easy to make assumptions that, this behaves the same as this, right? It looks roughly the same, right? This is just an implicit argument, but the multiplicities actually make a huge difference between the two functions, and yeah, you get completely different behaviors potentially. And you know, now I know not to trust functions that look like this. At least at face value, I have to actually look under the hood to see how they're implemented to make sure that they're safe to use. Whereas this one, I know absolutely, like, this one cannot do anything else but return the value that it takes in. So that's super duper useful to know. At least if you're an Idris programmer. Obviously, if you're just a mainstream developer, this is probably not particularly exciting to you. You're probably just like, whatever, I don't care. But this stuff on linearity, is very cool. The resource protocol stuff, yeah, this is the, like, there's a reason why they front loaded the stuff on resource protocols, because this is definitely going to be very useful for making sure that files are closed. There's a potential to avoid garbage collection. Like, that's pretty freaking cool. You can get better performance for free. What else? I guess, yeah, you could make sure, like, sockets are closed properly. Yeah, anything to do with resources, right? Like, that's the main reason for that. And I definitely feel like this is something I wish I could do in Scala, for example, where, when I'm, like, working with Spark or whatever, there are certain times where it's like there's like a file system close method, and you're like, I don't know, like, do I call that now? Do I have to call it now? Like, it's not particularly documented well, and it's just like, I don't know. Like, this is a way to enforce proper usage at compile time without having to, write the correct documentation for it. Like, you can, like, it's good to have documentation anyway, just to describe what it does, but at least, like, the way that you use it is absolutely clear just from the multiplicity, right? If it has a multiplicity 1, that means you have to use this thing, and you cannot use it more than once. You absolutely have to close that door, otherwise your program will not compile. So, therefore, if you had, like, a close method for your file system, for, like, Hadoop file system, you can guarantee that function has to be called with this one multiplicity. So that's really cool. I like that idea. I think that's very powerful stuff. And yeah, that's pretty much it for today. It's 5 p.m. I want to wrap up now. So yeah, if anyone decides to watch this once it's been uploaded to YouTube as like a VOD, then I guess thanks for watching. And I think next time I might do something a bit different. Maybe we'll do some Haskell, because I've been reading a book on architecture and design of functional programs in Haskell, or, well, just, yeah, programs, or functional programs in general, and it would be nice to kind of show off how that works, how you could, like, architect and design larger programs in a functional programming language. I'm personally, still learning myself, right? I'm fairly new to that idea as well, and it'd be a good way to practice. So maybe I'll stream that next weekend. We'll see. If not that, I might do a stream on Rust. I already do quite a bit of Rust stuff already, though, because I'm running the Rust meetups. So yeah, I don't know. Although I don't upload much Rust stuff to my channel anymore, so yeah, I don't know. We'll see. Leaning more towards architecture and design stuff, though, because that's more interesting and relevant to what I'm trying to learn right now. So, yep, that's it for today's stream.